All right, now let's try to take a look and see how well you know the definitions for circles. I'm going to suggest that you pause this video, try these problems on your own before we go over them together. All right, so you first want to name two radii in the circle. So a radius is from the center of the circle to a point on the circle. A radius could be AB. It's a segment, so you should be using the segment symbol. You could also have AF, that's a radius, and then AD is a radius also. You only have to have two of those, but those are the only radii drawn in there. I mean, if you said AC, that would be correct, even though that's not drawn. AE would work as well. You want to name a chord. So a chord could be EC. That segment has its endpoints on the circle. Even though ED is a line, if you just made it a segment, then that would be a chord as well. And then DF, I should have changed this question and name a chord. That's not a diameter because on number 3, you want to name a diameter, and then that would be DF. If you have that as a chord on number 2 as well, that would work. And then on number 4, name a secant. So a secant's a line that intersects a circle in 2 points. The only one that's drawn there, unless you made FD a line, is ED. It's a line, so should be putting a little line symbol above ED. Name a tangent. A tangent there is here. You're only given point B, the point of tangency, so you have to kind of name another point on that line, what's not used. So something like BT. BT is a tangent. And then the point of tangency is a point B. So those are the basics of circles for 1 through 6. And then if you tried number 7, how many common tangents the circles have, and then draw them. Since these two circles are congruent, they could share a tangent basically at the top. There's a tangent to both of the circles, and at the bottom. And then here's the points of tangency as well. So there would be 2 common tangents for those 2 circles. And then tell whether each common tangent identified in exercise 7 is internal or external. We kind of didn't talk about that, but I think you'd be able to figure that out. Both of these tangents are outside of the circles, so both of them would be internal tangents instead of external tangents. Sorry, I said that wrong. They actually should both be external tangents since they're both outside of the circle. Internal would be inside the circle, external outside of the circle. And then again, I'll ask you to pause the video, try problems 9 and 10 before we go over them together. So to find the length of BD, you have to use tangent to a circle theorem. Since BD, that line is tangent to circle A, then that means that AD, that radius, is perpendicular to DB. And then you could use the Pythagorean theorem. Since you have a right triangle, ABD, you have 2 sides of the right triangle, the hypotenuse and the length, then you could use the Pythagorean theorem. 5.5 squared plus BD squared, that length, is equal to 10 squared. And then you solve that equation. So 10 squared, 100, minus 5.5 squared, which is 30.25. You take the square root of that. And then if you round in the nearest tenth, after you take the square root, you should get BD is about 8.4 units in length. And then it tells you that point C is also a point of tangency. If BC is 4x plus 6, find the value of x to the nearest tenth. So BC is 4x plus 6. To find the value of x, you have to use the external tangents theorem. So 4x plus 6, the length of BC, a tangent to a circle from a common external point here, should be the same as the length of BD. And then on number 9, we found the length of BD, 8.4. So we could set up the equation, 4x plus 6 is equal to 8.4. And then solve that for x. Subtract 6 from each side, 4x is equal to 2.4, and then if you divide each side by 4, then x is equal to 0.6 or 0.6. That's to the nearest tenth.